Okay, now it's recording. So the previous question is cosine. One, how can we navigate that? Either a trigonometric expansion of these cosine expansions of summation of two cosines or multiplication of two cosines, etc. It's more complicated than that, but if you combine it, it becomes a simple cosine. Now, we can also motivate it like this. Let us take this angle argument here and say that theta, the angle is omega 1 t1 plus omega 2 t2. Now, on the t1, t2 axis, this is a line. This is the equation of a line. So for every, let me write it, for every angle theta, this is a line equation. Meaning that since the angles will be in the form of a line on this surface, the corresponding cosine of that angle will also produce a line. Okay, now Fethi is asking to come in. So Fethi, I was answering your question in a more rigorous way, if you're hearing. You asked why this was consisting of a one-directional cosine waveform, and I said I gave a few explanations, but probably the proper explanation is that because the angle term inside this cosine, which you can call theta as the angle, is equal to omega 1 t1 plus omega 2 t2, is a line equation. So for every angle theta, this is a line equation. Therefore, the angles are forming equal angle terms, are forming lines, and therefore cosines of those angles will also form lines.
Actually, maybe they call them hyperplane, since we are in continuous. Maybe it's more of a hyperplane. Maybe, I don't know.
Yeah, it's a surface. It's not a plane because it's not straight. It's not hyper because it's only three-dimensional, but it's a three-dimensional surface we're talking about. And that three-dimensional surface waveform consists of a cosine with angles corresponding to line equations on the t1, t2 axis, which are the coordinate axis of that image, of that function. So if the coordinates form a line for the angle, or the cosine of that angle, it also forms a line. Because omega 1 t1 plus omega 2 t2 is equal to theta is a line equation. Okay, so I think this is maybe a more proper way of putting things. I just couldn't think of it when you asked the question, but while drinking my tea, which I couldn't finish, I realized that I should give this kind of an answer. Sometimes you need some sugar for the brain to function properly. All right. Now, so we were talking about the linear and shift invariant systems. There are some further desirable properties of linear and shift invariant systems. Maybe first let's start from the one D can be thought of as a superposition of impulse responses. So we have impulse responses separately, and then we scale them according to the input, and we add them up. That is a way to calculate convolution, but it's not practical, especially for continuous time convolutions, because we cannot isolate the input outputs separately, and we cannot combine them separately because it's a continuous convolution. We have an integral instead of a summation term. So You remember what we were doing in continuous time convolution? We were folding around one of the signals, let's say the impulse response, and we were sliding over the input signal, and we were just multiplying at every shift of this slide. At every shift, we were integrating or multiplying, and the multiplication is integrated. And we were discovering a methodology to find the convolution output. Now in 2 dimensions, that is also possible. In other words, if you have, and it can be also in discrete time as well, so not necessarily only in continuous time, but if in 2 dimensions, discrete or continuous, you have a region of support of this, for example, which is the size of the image, like N1 and N2 are the limits, let's say, over the horizontal and vertical axis. And suppose we have a convolution impulse response or point spread function in this form. So what you can do in order to convolve in 2 dimensions, these 2 functions, you can still fold one of the signals, but not only horizontally, but also vertically as well. So this one would be first folded into this after horizontal folding. So this is horizontal folding, but a vertical flip is also necessary. So by vertically folding again, you will now come up with this shape, okay? So in general, or in short, you will fold it twice around the origin or something like that to come up with this one. And then you can slide over the other image and you multiply. Of course, what you are multiplying would be the values, okay? The value of this at this coordinates, let me put a red dot here. This red dot, this coordinate may be A, and then you will just need to multiply that A value with the separate A, B, C, D values in the original rectangular, as I have illustrated, image. So folding and sliding over the other one is a way to make convolution in 2D. It's also a methodology to apply convolution, not only superposing impulse responses, but also doing it this way. This may be even more useful for continuous time images, as I say, surfaces, because there you will find the volume under the surface of the multiplication of 2 surfaces. It will produce a surface, and there is a volume underneath, and you have to evaluate the volume, not the area. But these are technical things. In many cases, the H is something like this. For example, a 3x3 filter. Filters are usually short because of computational things. This convolutional template, for example, if they are all equal to 1/9, that would correspond to an averaging filter, a blur filter. All of them are 1/9. So it's like blurring throughout the image when you apply. And if you fold it twice, it will give you the same shape because it's around the origin. The origin is the center pixel here. So this is some sort of a low pass filter, you can say. So convolution works like this. For those of you who are more familiar with modern and newer technologies, you might have heard about convolutional neural networks. Okay, is there any of you who haven't heard of any deep neural networks and convolutional neural networks in this room? Is there anybody who hasn't heard of convolutional neural networks? No one is saying anything. So I believe you have all heard about that. The reason that it is called convolutional is because the connectivity from one layer of a neural network to another layer of a neural network is not fully connected. I mean, the input image is a large image, and the output of the next layer is also the same size large image. And from here to here, normally regular neural networks have connections from every pixel. They are connected like this. For example, this is 4 by 4 input, and the output is also 4 by 4. The next neural layer, and for the function for this red point, actually all of the pixels from the previous layer should be connected. I'm trying to use separate colors like this, and finally, let's be precise, like this. So it's a mess. Even for this particular red pixel, as you see, everything is connected, and they are weighted by some weights. Of course, the connections have some weights, and afterwards, this pixel that point, the red point, takes the sigmoid of it, or takes the maximum of it, or the minimum of it, or whatever. Okay, doing something with that weighted coming data, separately coming data, or it may just add them all, or do something like that. This thing is not done in deep neural networks because images are large and layers are many. So if you try to do it this way, your computers will not be capable of doing it. That is one point. The other point is that images have local features. If we're talking, not general, I'm not talking about general two-dimensional signals, but if it is an image, notice that my finger is here, and my finger, the pixels corresponding to that are near to that. My nose is here, and the pixels around there is near to that. And my sweater is here, and the dark pixels are nearby, the books at the bookshelf. So there are local features. So instead of connecting all of that, what they did is they say, let us think of these only to contribute to the corresponding pixel, let's say this one, which is around that pixel in the previous layer, something in the local neighborhood. So if everything is in the local neighborhood for the corresponding next layer point, then every point is generated by actually weighting the pixels in the previous layer, or the points in the previous layer, which are this, and this, by some weights. And then you are just sliding. So what does that operation mean? It means convolution. That's why you are convolving with a weight point spread function, this red bounding box, throughout this image. Slide it all over the image, and then produce the corresponding output pixels one by one. That's why the name is convolutional. And there are two reasons. For one, it is not as complicated as totally connected. And second, for images, total connectedness is not necessary because features are locally correlated in terms of pixels in images. Hence the name, okay, convolutional neural networks. So this was a crash course on convolutional neural networks maybe, but it's not, of course, convolutional neural networks that I'm explaining, I'm explaining why they are using the term. Okay, now the next about the 2D systems is separability. It was left as red, so let's make it black. So separable linear shift invariant systems. Separability of a process, of a two-dimensional process or a filter, is a desirable property because it greatly reduces the number of operations. In a separable system, it means actually the system was 1D, and then we applied it horizontally and then vertically. Therefore, it became a two-dimensional process. And for that, you need to have, where is that? Okay, you need to have h of n1, n2, this two-dimensional filter, to be equal to h1 of n1 times h2 of n2. So if you can express the numerical or analytical expression of your two-dimensional point spread function as a multiplication of two one-dimensional impulse responses, then it means that your system is separable. Usually things are the other way around because we have excellent digital signal processing tools to construct one-dimensional filters with good frequency characteristics, like the low-pass region, high-pass region, or stop band region, etc., with some certain frequencies at a given particular length. So we better know how to design in 1D. So if you can come up with a good filter in 1D, what you can do is, let's apply it to an image. How? Let's apply it horizontally to the image, and then the output we apply to the vertical process. So it will be a two-dimensional process that we do. We don't usually try to find the separable components of an already two-dimensionally designed filter. Two-dimensionally designed filters are, of course, they have better degree of freedom. They may be better fine-tuned to your image. So you don't expect them to be separable. You don't try to separate them. But if you design already in 1D, you just apply horizontally and vertically, and that corresponds to a separable process. And the other one is stable LSI systems. Stability is not a question in image processing in many cases, because images, or digital images at least, are finite. They have finite height and width, and they have finite values. So whatever you do in a process, in a linear system, of course it will be a bounded output. It will produce a bounded output. So that's not important. But if we are talking about two-dimensional systems instead of images, of course stability is an issue. But if and particularly for those that are infinite impulse response, because there is a pole, because there is a feedback loop that is processing the output again and again. Such systems, as we know, if there is a pole, if there are poles of a system, then stability is an issue, as we all know. And for the stability, for us, in our side, if we will keep it simple because it's unimportant, we will just say that if the point spread function of h of n1 and 2 in absolute values summed up for all n1 and n2, if this is less than infinity, we will say it is bounded input, bounded output, Bibo stable. And if the summation for the square of it if the square of it is finite, we say it's mean square stable in the mean square sense. What kind of a stupid mind would produce an impulse response or a point spread function that extends to infinity? So most of our systems are already stable, and we don't really need to even care about this in image processing. But of course, you are doing you may be taking this class from all sorts of disciplines, and you may be just curious about what is this image processing. So you may think of this as a systematic way of looking at two-dimensional signals and systems, and you may find this beneficial in multi-dimensional cases. And the stability issues are all the same. Okay? This is also valid for one dimensions. Now, I will very quickly skip to the new page, and I want to talk about the final thing here. We will continue talking about this. Don't worry about that. So this will be a little bit fast because I'm running out of my own time for another process of mine. And that is the frequency space. That is the Fourier transform I'm talking about. The linear and shift invariant systems and the concept of frequency space or the Fourier transform go side by side. Without the linear and shift invariance and such properties, it's actually meaningless to start to try to look at the frequency. We cannot even talk about the Laplace transform or the Fourier transform or any kind of frequency response or anything for nonlinear systems. If somebody asks you a question regarding what is the frequency response of this nonlinear system, you have to just put a cross over there. This is a nonlinear system, and for nonlinear systems, we cannot talk about frequency. The reason that it is available to linear and shift invariant systems is because linear and shift invariant systems have eigensignals, which is equal to e to the j omega t. Let me first briefly introduce what's happening in 1D. This is the input system to an h, which is linear and time invariant, let's say. I'm talking about only one dimensions. And the output is a constant which depends on the frequency only times the same function. So doesn't it resemble this equation? A matrix times x is equal to lambda times x. You may ask me what's going on. This is linear algebra. But actually it is, this A matrix here is the filter. It's the process that is filtering the input, which is x vector. And after the filtering, the output is the x vector itself, just scaled by lambda. Okay. Do we know what these x's are for this kind of a system A? What is the relation between A and X, in other words? Do you remember that from linear algebra?
Eigenvector.
Yes. X is the eigenvector of A. It must be an eigenvector of A. And when you look at this, what you really see is that complex exponential e to the j omega t, which is a sinusoid, by the way, right? It's consisting of a cosine and a sine term, an imaginary sine term. So they are actually sinusoids. Complex sinusoids in general, it may be real sinusoids. Complex sinusoids are eigenfunctions of linear shift invariant systems. These are eigenfunctions of LSI or LTI systems, because they go out the same. That's where we all start. And then we continue with the definition of a signal. We extend this like from here to here. We say let's try to write everything in terms of e to the j omega t for different omega. So it is omega from, let's say, minus infinity to infinity. What kind of a notation should I use best? That's what I'm thinking. But because my notes are all in discrete time, and now I'm doing it in continuous time. But anyway, this is x of omega e to the j omega t d omega. This is, let's say, the inverse Fourier transform. It is indeed the inverse Fourier transform within a factor of 1 over 2 pi or something like that, but let's forget about that scale for the time being. Let's incorporate it into x of omega. So I am combining different frequency complex sinusoids. It's like this thing to be written as e to the j omega 1t, or a times e to the j omega 1t plus b times e to the j omega 2t plus c times e to the j omega 3t, etc. I'm expanding my signal into separate complex sinusoids. What will be the output of this? Or how will we find the determine the output? First, let's find the output to one complex sinusoid, which is this one, the original one. And for that, let us do the convolution. I haven't done this for ages, but I'll try to do it right now. I'm trying to convolve h of t and e to the j omega t, and see if really the output would be e to the j omega t times something. And the convolution I will make will be h of tau times e to the j omega t minus tau d tau. The convolution in the integral form. You remember this? You may remember that from signals and systems. If you don't, please remind you about the formula for the convolution. H of tau, x of t minus tau. That's what I'm writing. You could write x of tau, h of t minus tau. It doesn't matter. The convolution can commute. So this is also equal to integral h of tau e to the j omega t times e to the minus j omega tau d tau. Okay? And that is equal to, now this e to the j omega t part is independent from tau, so it can be taken out of the integration of tau. It's not related with tau. So I'm taking it out. E to the j omega t times integral h of tau e to the minus j omega tau d tau. And believe it or not, we are finished, because I said that the output of this convolution will be e to the j omega t times something. And it is now, that's times something. And times something is this. And there is a name to that times something. What is it? We can make it a very short term. Integral h of tau e to the minus j omega tau d tau. If you don't understand what it is, think of it like this. Integral h of t e to the minus j omega t dt is the same. Just change the variable to something that you are familiar with. But tau is okay. So what is it?
The Fourier of the, like,
yes?
System?
No, it's the Fourier transform of h of t.
Yeah, system like h.
Yeah. It's the Fourier transform of h, which
Yes.
can be represented as capital H of omega, if you wish. right? It's the Fourier transform. So the output is therefore h of omega times e to the j omega t. In the beginning, what did I say? I said that it is a sub omega, which is a function of omega times e to the j omega. And now I found what it is, that a, it's this, right? So we got it. We know the output. It is h of omega. So in the previous expression at the left-hand side, I'm talking about here. Now let's take one by one, or find one by one the outputs of each of these inputs. What is the output to a times e to the j omega 1t? The output will be a times h of omega 1 times e to the j omega 1t. To this one, it will be b times e to the j, sorry, first let me put h. Let's be consistent. H of omega 2 e to the j omega 2t, and to this it is c times h of omega 3 times e to the j omega 3t. And then the output will just combine these, and this will be the output y. But I will continue that y starting from here. Now let me go back to black. If x of t is this, okay, then correspondingly y of t will be the same combination of the output of each of these individual components inside the integration. So to each e to the j omega t, I will have h of omega times e to the j omega t, okay? To each e to the j omega t. This is what I will have. And to each x omega times e to the j omega t, I will have x omega times h of omega e to the j omega t. Because of linearity, if I scale, then the output is also scaled in the same way. And if I accumulate the input using an integral, the output must also be accumulated. Okay, this is what y of t would become. This is what the output would become for a linear and time invariant system. And we know that, by the way, using the inverse Fourier transform, this is equal to y of t is equal to, in other words, y of omega e to the j omega t d omega. Let's not forget the d omegas here and here. Okay. This is by definition. The last one is by definition, which means that this must be equal to this. So y of omega is equal to x of omega times h of omega. This is the convolution versus multiplication way of looking at things. So if you are convolving x with h to find y, you can do the same in the frequency domain by multiplying capital X, the Fourier transform, capital of X with capital of H, multiply them to find the capital of Y. Okay, that is the filtering in frequency domain. So in 2 dimensions, that's the same. In other words, if y of t is equal, oh, no, it's not t. Let's say y of t, like this, is equal to x of t convolution with h of t, then y of omega, now look at the bar. I didn't give the expression for this one yet, but you can understand that it's just a 2-dimensional extension of the same Fourier transform formula. without much changes, except the 1 over 2 pi coefficients in either the inverse or the forward Fourier transform will now become twice, because one integration requires 1 over 2 pi, the other integration of the formula also requires 1 over 2 pi. When you multiply them, it will give you 1 over 4 pi square. That's an oddity of the two-dimensional extension of the Fourier transform formula in the formula. But whatever that formula is, again, it happened. Y of omega is equal to capital X of omega times capital H of omega. So convolution versus multiplication still acts the same way. By the way, it may be a good idea to give you the formula for the two-dimensional Fourier transform in discrete time, particularly because image processing requires the two-dimensional discrete time Fourier transform in many cases. But I am running out of my time for another appointment of mine, which makes me stop at this point. We have done quite a lot anyway, so we will meet again next week in the same day and the same hour of 9:30, okay, again. We will continue from there. Do you have any quick questions up to this point? Because now I will be stopping the video.
Sir, when should we present the project proposal?
When should you present? As soon as possible. That's a personal communication among us. You may email me about what you will be doing. If you may request a Zoom call or another way of making a chat, that's also possible. We will discuss a little bit, and it must be image processing related way of looking at a topic, but it doesn't have to be pure image processing. I mean, it doesn't have to be image processing for the sake of image processing, but you may have some applications as well.
I see. Okay, sir. Thank you.
Which benefits from image processing tools and things like that. That's also possible. It can be the other way. It can be purely image processing. But if you come up with an idea that we will be already discussing in our classes, I will tell you not to do it. Or I may ask you, on the contrary, to come up with an animation way of explaining things, or even a telephone application, which runs it in an animated way where the students may benefit for understanding purposes. That's also possible. It's another project idea, right? Yeah. You have to contact me personally about those.
Sure.
All right. So now I'm ending the recording.